Okay, this mini lecture is going to look at the idea of thermal expansion. And so when most substances are heated, they start to expand. And I'm sure you have experience with this. For example, if you are walking down the sidewalk, you see that those concrete blocks are laid in squares with tiny little gaps in between them. And those tiny little gaps are so that with the temperature changes from really, really cold in the winter to really, really warm in the summer, that the concrete has the ability to have room to expand. So as things heat up, they tend to expand. And so this is going to look at how we calculate that expansion and what is it dependent on. So microscopically, we have these molecules that are starting to spread apart. And so when they do that, the material will change its length. So you might imagine that if I have a rod and I increase the temperature of that rod, we get a small change in that rod's length, delta L. And that change in length is the result of these molecules spreading out. Now, I'm going to fix this side, but every molecule along there is spreading out. I mean, if this was free, we might see it spread in both directions. It's not, I just want to make sure we're understanding, it's not just spreading in a single direction, it's the overall length that metal rod is expanding. Now, what might affect how much it expands? Well, we said temperature certainly plays a role, right? Thermal expansion. So if I change the temperature, I would expect to get a change in that length. A bigger change in temperature, a bigger change in length. So I might expect that is proportional. What else might affect how much a length change I get? Well, the original length, what we're going to call L naught, influences the change in length. Okay, so L naught, I'm just going to put L naught. L naught, the longer the object, the bigger the change in length I'm going to get. Why might that be? Well, if you imagine this bar expanding in both directions, a smaller bar will also expand in both directions. There's more molecules in that bigger bar. So there's more molecules expanding, it can expand even more. So the original length makes a difference. Second is maybe how much those molecules are, how much those molecules are interacting. And that's a property of the material itself. And we call that property, we use alpha. And this is what we call the coefficient of linear expansion. And this is dependent on the material. It is a property of the material itself, okay? So steel has a different coefficient of linear expansion than aluminum, for example. So this is the property of the material. Okay, now, when we look at all of these relationships, we find the relationship for linear expansion so our change in length is equal to, we tend to use a lowercase l for this, is equal to our coefficient times our initial length times our change in temperature. All of the things we said were important. Okay, all the things we said were important. This leads to another, so this is the base equation, but actually we can rewrite this equation in a different form if we recognize, of course, that the change in length is equal to a new length minus length naught, right? Final length, any change, final minus initial. And I can write the linear expansion equation just looking at the absolute length. What is the new length of my material? And it is 1 plus alpha delta t. So now I can look at both the change in length, or I can look at, I forgot. Whoa. I made a mistake. Sorry. Should be on that. I'm like, that doesn't look right. I can look at the linear expansion as a total overall change using the first relationship, or based on the definition of what change means, I can look at what is the length I end up at given the parameters that affect linear expansion. Okay, so that is how we think about an object expanding linearly, the length changing. Now, how can we use this idea to our advantage? Okay, and one of the misconceptions of linear expansion is if I have a ring. If I have a ring and linear expansion, I heat that ring up, what happens to the hole? And I want you to be attention that, like, let's think about this as the length that's going to expand. Okay, to help you remember, the hole gets bigger. The hole gets bigger. And if we think of this as the length of expansion, that might help us visualize it. As if we were to unwind this tube, for example, and put it through linear expansion, it would get longer. And if I were to reattach those two ends, I have a bigger hole. So that's one way to think about it. The other is that this is expanding out. This is getting a larger distance. Another way to think about it. But how does this help us? Well, if you ever had a really stuck jar, you can't get open that jar, what do? You heat it up, right? You run it under hot water. And what happens when you run it under hot water? Pops right open. That hole has gotten bigger. All right. Just a little kind of reminder there of using our physics in a way that really helps us practically. Now, in addition to linear expansion, you might think, well, what if I have this solid material and I have a chunk of solid material and it's going to kind of expand in all directions, or I have a liquid that's going to kind of expand in all directions. So we can also talk about volume expansion due to temperature. And it's identical to linear expansion. Our change in volume is going to be dependent on the property of the material. And now we're talking about that property in a different way. It's going to be the coefficient of volume expansion, beta, to the coefficient of volume expansion. As you might imagine, times that initial volume matters sort of how much material we have to expand times the change in temperature. All right? So again, keep in mind that this volume expansion is a property of the material, right? So it's going to be different for each different types of materials. So here are two representations of thermal expansion that we're going to use. Kind of have two ways to think about linear expansion. You can do the same thing with volume expansion. I'm not going to go through that process again. It looks the same. And for nearly all materials, this is how they operate. Of course, there's one exception to the rule. Always is, right? One exception to the rule, and that's with water. I'm not going to go into a lot of detail of water's exception, but I will tell you, exception, that it has one, particularly between 0 degrees and 4 degrees Celsius. It's right at that freezing point, okay? At that freezing point, when water is heated up between 0 and 4 degrees, it actually decreases in volume. It's a unique property of water, it decreases in volume. It's really useful and functional for us, and you can go ahead and read on how that's super important for aquatic life and how it causes ponds to freeze top down instead of bottom up. But water is that exception, and furthermore, as water converts to ice, it also expands. So as it even cools more and freezes, we get an expansion. So water's an exception to the rule. Most other things operate in this idea of thermal expansion. So we're going to do a couple practice problems. You can look at those videos, one for linear expansion, one for volume expansion. All right, good job.